Vabbè, mi chiudo,
Mi sa che perché 60. Hai fatto una numero, non so. Mi sa perché...
È quella?
Sì,
no, mi si è chiuso.
Come dici? No, mi sembra che ci fossero due webcam, ma giustamente lo dice quella a 360 massimo.
Sì.
Ok. Ok, giusto.
Hai preso... Hai preso... No. 60.
Dice che su team con
Prima la vita non sono capace di ammetterlo così.
però perché sei entrata tranquillamente. Guarda un po' partecipanti.
Non riesco a... Non tocco niente, qua se lo faccio vedere.
Ma sa che secondo me non è sbagliato.
Non la manca niente. Tu sei più avvezzo. Sei andato di Ziano, ha smesso di...
Ma no, ma che... Allora. Ci ammazzo.
Sì, no.
Ma che... Ah, ok.
Non li mettiamo schermi interi.
Ma dove stai? Di che? Cos'è? Immagino.
Vediamo, no, sto a mettere io.
Ok. Secondo me ci siamo.
Fammi provare ad aggiungere.
Can you try, Alexandru, if
The slides are working or
When the slides are...
is it sliding?
Yeah.
Yes.
There's
Okay.
yeah.
Aspetta, lo faccio un attimo.
There's a little bit of a delay, but yeah.
Aggiungo io.
It doesn't.
Well, if you start working, then it will react faster. If you wake him up.
Ci sono anche io, ma chiudo il microfono.
Bene, ciao Andrea.
È lui che fa casino.
Ciao Giovanni.
Ciao.
Avrà riconosciuto la tua voce.
Si parla male di te qua.
Strano.
Sì, ho sentito anche la voce Simona.
Quando uno ti vuole bene.
Beccata.
Ok. I think... what is this now? Okay, you better start. Ale, please.
Okay, so good morning everyone. Welcome to today's episode of the seminars at Iasi CNR. Today's speaker is Alexandru Hening. Alex got his PhD from the University of California, Berkeley in 2013. And then he was a postdoc at Oxford University and a Chapman Fellow at the Imperial College. And after some a visiting professorship like in Sydney. He finally landed at the Texas A&M University, when he's currently an assistant professor in the Department of Mathematics. His research interests are in the stochastic processes, mathematical ecologies, and dynamical systems. He's an editor of many leading journals, of some leading journal in the field of mathematical biology. In his young career, he's been also recipient of a number of awards and grants. In particular, he's currently a PI on a grant from the National Science Foundation about dynamics and harvesting of stochastic population. And today he will talk about the modern coexistence theory, which I'm sure will be a topic of interest both for the more theoretical and applied mathematics among us. So I think we now can give the floor to Alex. Welcome, and please.
Thank you very much for making it possible for me to give a talk. Very delighted to be here. So I'll be talking today about some of my work on population dynamics or modern coexistence theory. So what do people care about in ecology or in population biology? Well, one of the most important questions is trying to figure out when interacting populations coexist. Usually you have a very complex ecosystem of interacting species. There's predator-prey behavior, competition for resources, mutualism, and so on. You have all these nonlinear effects, and the question is, what happens long term? Which species will persist? Which ones will go extinct? Okay, well, what does a theory need to take into account if we want it to be realistic? Well, we have to take into account all the interactions between the species, of course, but we also have to realize that all these ecosystems have inherently some type of randomness. There are environmental fluctuations in them. You cannot predict the rainfall, the sunlight, all these factors are random, and you need to take this randomness into account if you want realistic models. So one of the most well-known and well-established theories is modern coexistence theory. So it's been developed by Peter Chesson in the late 80s, and it's very widely used by ecologists. However, there are some shortcomings of modern coexistence theory. For example, one needs to assume that the environmental noise has small fluctuations. So the variance, the environmental variance is small, which is not usually what one has in nature. And there are only rigorous mathematical results when there are two species. Whereas, of course, most ecosystems have tens, maybe hundreds of species. Okay? And furthermore, there are not many results for extinction. So the results that were available were mostly for when species coexist. But we also want to know if species go extinct. We want to know exactly which species go extinct. So Chesson and Elner conjecture in the 80s that their results should be able to be generalized to ecosystems with any number of species. And since then, there has been progress, but usually in specific settings. So our goal was to come up with a rigorous mathematical theory that can cover a very wide variety of settings. Okay, so what we did was we generalized modern coexistence theory. We were able to include large environmental fluctuations, and our results are rigorous for any number of species. Not only that, but we have results both for coexistence and extinction. Okay, so, and even though I won't present all the different types of settings that our theory works in, it works both in discrete and in continuous time settings. There are various types of ways of incorporating noise, and you can work in compact and non-compact state spaces. Okay, so let's start with the simplest model. You just have one population. The dynamics is governed by the simplest differential equation, right? You You just have that, you have exponential growth or decay. So this differential equation, x is the population abundance or the population density at time t. Here you can solve this explicitly, of course. So you have x of t is x of 0, the initial population size, and then times e to the rt. So what we are interested in, you'll see, is we'll be looking at the log of the population divided by time, and we'll let time go to infinity. Here, of course, this will be equal to r. So r is the log growth rate.
x0 r,
x0?
x0 multiplied r. Right?
No, because the x0 divided, it will be divided by t. It will be log of x0 divided by t. It will go to 0.
Okay.
Yeah. But yeah, if you wouldn't take the limit, yeah, you'd have an x0 term as well.
Right.
So now one way of introducing noise is saying that, well, the growth rate, this r, is not actually fixed. It has some fluctuations around its average. So r is the average, or the expected value, and then you have some white noise fluctuations around that. And the variance will be this sigma, or sigma squared. Okay, so this white noise transforms the previous system of the previous ordinary differential equation into something called the stochastic differential equation. So now instead of having, we have this extra term in red, which is due to the noise. So now this b here is a Brownian motion, and we have sigma times x. So in a way it's linear, it depends linearly on x here. So it's a linear type of noise. Okay, you can still solve that stochastic differential equation explicitly, but we don't care about the explicit solution. What we care about is, again, we want to look at log of x divided by t. And now, because it's a stochastic differential equation, you get an extra term if you use Ito's lemma. So instead of getting log x over t converging to r, it converges to r minus sigma squared over 2. So the noise here decreases the stochastic growth rate by this sigma squared over 2. And you can easily show that if this term is negative, the population goes extinct. But the extinction means as time goes to infinity. So in none of these settings will we have extinction in finite time. Extinction will only happen asymptotically. Okay? And if the stochastic growth rate is positive, the population will blow up. Now, of course, it's not realistic biologically to have that the population blows up to infinity. Well, we can amend that, right? We can add a term which takes into account that resources are finite, they're not unlimited. So you can add this competition term, this term in red, in the drift. And what happens here? When the population size becomes very large, this term here becomes very negative. So you get a drift, you get pushed back towards extinction, right? If the population tends to blow up, well, then there will be no more resources and it will start to die. And what's interesting is that even though now this is nonlinear, right? It's become quadratic here, the drift term. The same r minus sigma squared over 2, the same stochastic population growth rate fully determines the long-term behavior. So if this is negative, you get extinction. And now when it's positive, you don't get the blow up anymore. You actually get coexistence. You get that there exists a unique invariant probability measure or a stationary distribution, and the population converges to this invariant probability measure. And you can think of an invariant probability measure as the random analog of a fixed point or an attractor. Instead of converging to a fixed point or an attractor in dynamical systems, you converge to this random fixed point or random attractor. Okay. So what's key here is that this stochastic growth rate, r minus sigma squared, determines whether the system persists or goes extinct. And it's sometimes called the invasion rate. So ecologists call it an invasion rate. You will see that one has a background in dynamical systems. You could call this a Lyapunov exponent. So there are different names for this. Okay, now let's go to the general version of the problem. So suppose we have an ecosystem of n interacting species now, right? So bold-faced x, this x now will track the n different species. So x1 of t is the abundance of species 1 at time t and so on. And then if we just look at the deterministic dynamics, we'll have this nonlinear system, which tells us here, if we focus on species I, that the per capita growth rate of species I is just given by this function fi, which can depend on all the other species, right? So it can be highly nonlinear, right? All the different interactions between the species and so on. Okay, now one way, and I'll tell you about another way later in the talk, of adding noise is, again, just doing the same thing we did before. We say, well, instead of some of these parameters being fixed, they fluctuate because of white noise. So your system of differential equations becomes a system of stochastic differential equations. So the blue terms are due to the noise, and now the EIs are various Brownian motions. So each species is driven, like the noise is given by a Brownian motion, and there can be correlations between these Brownian motions, or you can, the simplest setting would be to assume they're all independent. Okay. Now we need to define what we mean by persistence in this deterministic setting. So one definition of persistence is persistence in probability, which was introduced by Chesson in the late 70s. And what it means is that with high probability, the species is bounded away from extinction. So because of these stochastic effects, usually the population will get close to zero, and then it will go back up, and then it gets close to zero again, and so on. So that's why it's not, usually it won't be that with probability 1 you're bounded away from 0. You keep going back, but you can make the probability as close to 1 as you want. Okay? Or a stronger version of persistence is the existence of an invariant probability measure or a stationary distribution. So not only do you not go extinct, but you converge to some type of random equilibrium, this invariant probability measure. So an invariant probability measure is defined as follows, that if you start x with that distribution, it will have that distribution forever. So just like if you were in the deterministic setting, if you have a fixed point and you start there, you just stay there. But now it's random, right? So, okay. So what's the intuition? Let me tell you about the intuition. Suppose you don't have all your n species present. You have a subcommunity of your n species. We call it M. And now suppose that this subcommunity of species coexists, right? And their coexistence will have some invariant probability measure. So the random equilibrium of these species from capital M has an invariant probability measure mu m. And now we want to introduce a new species, I, into this, right? So we want to introduce this new species. We know it's governed by this stochastic differential equation. And what we do is we take the log of xi and divide it by t. And because, again, we're in this setting with stochastic differential equations, we get an extra term here, right? From Ito's lemma, you get this extra term. And what we want to do now is want to take the limit as time goes to infinity. We want to see what happens with this log growth rate. This term here, of course, will go to 0. This third term, one can show that if gi is well behaved, it's a nice function that doesn't grow too quickly. This term also goes to 0. And the only limit we will care about is the limit of the term in red. So this term in red will determine what happens with xi. Okay, so what will happen? Well, if xi stays close to that invariant measure mu sub m, so this invariant measure mu sub m, remember m doesn't include all the species. So mu sub m lives somewhere on the boundary, right? So if we stay close to this invariant measure, then by ergodicity, you can show that this average, right, this complicated thing, this integral average, is approximated well by this integral here, which is just a number now. It doesn't depend on time anymore, right? This is just basically this is the average dynamics. You average the dynamics of I according to mu sub m. So if mu sub m would just be one species, and it would have a fixed point somewhere, this would be a Dirac mass there, and then you just have to evaluate this quantity there, right? So to see whether that fixed point is repelling you or attracting you. Okay, so as I said, the first and third terms there go to 0, and what will really determine the long-term behavior will be this Lyapunov exponent, or this invasion rate, where you integrate this term, you average it over the random equilibrium given by that subcommunity. So in a way, what you do is you introduce this species at a very low density, right? And then it's like when you have a fixed point and you linearize, right? When
What is the Rn plus? Rn plus, what is?
This is the boundary.
What boundary?
The boundary of
Rn.
Rn plus, right? Of the positive positive.
The hyperplane positive.
Yes. Yeah.
Hyperplane.
Yes.
Coordinate hyperplane.
Yes. I mean, you can integrate it over all of Rn plus, but the measures we care about will all be supported on the boundary. So this is exactly like linearizing around the fixed point, right? If you want to know if your fixed point is attracting or repelling, what do? You linearize around that fixed point and see if that linearization pushes you away or attracts you. And now we do the same thing, but we linearize around an invariant probability measure instead of a fixed point. So in our first example, here, when there's only one species, the only subcommunity which doesn't include that species is the subcommunity where everyone is dead, right? So the subcommunity where every species is extinct. So that's the simplest invariant measure of the system. It's the Dirac mass at 0, where if you start at 0, you stay at 0. So there, if we compute the Lyapunov exponent, we get exactly mu minus sigma squared over 2, which, remember, was exactly what was determining our long-term behavior. Okay, so intuitively, if this invasion rate is negative, it tells us that if introduced a species at the low density into that subcommunity, it tends to decrease. If it's positive, it tends to increase. So in terms of dynamics, it means if your process gets close to the boundary, gets close to this invariant measure, well, if this happens, it means you get attracted in direction I. If this happens, it means you get repelled. You get pushed away from the boundary. Okay, so then we're able to prove this theorem for coexistence. So what's the result? Suppose that for any subcommunity you take, so we take any subcommunity of the n species, if that subcommunity has an invariant probability measure mu sub m, and if there exists at least one species I which can invade that subcommunity, so at least one species which is not in that subcommunity which has a positive invasion rate, then we can show that the n species coexist. So basically, intuitively, what this means is whenever you get close to the boundary, you get pushed away from the boundary in at least one direction. So that's why nothing can go extinct, because we cannot converge to the boundary if you always get pushed away from it. So that's the coexistence result. Okay, so now I'll tell you how we were able to use our results to resolve this conjecture of Pallas. So we know that dynamical models are very important, and they're used not only in biology, but in physics, economics, and so on. And usually when you have a dynamical system, you want to be able to say what happens long term. You want to classify the possible behaviors of the system, right? The long-term behavior. And Pallas conjectured that at least if you have ordinary differential equations, typically what happens is, so even for deterministic systems, you can look at stationary distributions or invariant probability measures. Usually there will be a finite number of stationary distributions or invariant probability measures, and these will fully characterize the long-term behavior. So he conjectured that the long-term behavior should be characterized by these invariant probability measures. So we were able to prove this conjecture of Pallas in a setting where you have three species, you have three interacting species, and they interact according to this very general system of stochastic differential equations. So we're able to show that if you have three species, the long-term behavior is fully determined by a finite number of invariant probability measures. Now, some people might say, well, why is it so special that you can solve this conjecture for three species? Right? It sounds a bit trivial. Three species, it should be easy. But actually, this classification is still incomplete in the deterministic setting. So when you have three interacting species, even if you just look at Lotka-Volterra interactions, so the simplest type of interactions, you cannot say, or at least it's incomplete for now, what happens long term, what are all the possible long-term behaviors. So it was quite nice that we can say exactly what happens when you have three species. So now I'll give you the classification. I'll tell you what are all the possible types of behavior if you have three interacting species modeled by stochastic differential equations. So the first possible result is all three species survive, right? So all three of them persist. So that's what happens here. You start inside the positive orthant, and then you converge to something, you converge to a unique stationary distribution, which doesn't put any mass on the boundary. So nothing goes extinct. You converge to this random equilibrium, this cloud, right? Okay, what's another possibility? Well, you start here, and you converge to the x1 axis. So you converge to a unique stationary distribution, which is supported by the x1 axis. So species 1 persists, everything else goes extinct. Right? That's what this is. Or you start here, and with a certain probability you converge to the x1 axis. With 1 minus that probability you converge to the x2 axis. So either species 1 persists or species 2 persists. But no matter what, species 3 will go extinct. Okay? And then you can see what other combinations you have. Here, you converge to one of the three axes. But the probability will always sum up to 1. Right? So, for example, if you start very close to the x1 axis, there's a much higher probability you converge to that axis, and the others will go extinct. Okay, what's another option? You converge to the x1, x2 plane. So you converge to a stationary distribution which supports species 1 and 2. So species 1 and 2 survive, species 3 goes extinct. Or here, with a certain probability you converge to this space, 1 minus that probability you converge to the x3 axis, right? So either species 1 and 2 survive, or just species 3 survives. And then you see there are different options. Right here you convert to x1, x2, or x2, x3. Finally, you converge to one of the three faces. But those were not that interesting. So the last result is that you don't converge to any of the axes or any of the planes. You converge to a random equivalent of a rock, paper, scissors system. So what happens here? You start here, and then it looks like you're converging to the x1 axis. But x1 is defeated by x2. It's outcompeted by x2. So even though it looks like you're converging to x1, then you move, and it looks like you're converging to x2. But x2 is defeated by x3. That's why it's rock, paper, scissors, right? So then you go from here, you move to x3, and you keep cycling. So you keep moving. It's the stochastic analog of a heteroclinic cycle, right? So you keep moving between these and cycling without converging to any of the three axes or any of the planes. So this is the most interesting type of behavior. And this is all that can happen. Of course, I mean, I listed up to permutation. You can converge to a different phase, but So what's interesting is that you get this type of rock, paper, scissors dynamic. There's a cute example from nature where you have 3 different types of lizards competing for females. So there are aggressive lizards, furtive lizards, and guarding lizards. So the aggressive one gets defeated by the furtive one. The furtive male acts like a female, so the aggressive one gets tricked because he doesn't realize that that's not the female, it's a male. Then the furtive one gets defeated by the guarding lizard. The guarding one is always next to the female, so he cannot be tricked by the furtive one. And then the guarding one gets defeated by the aggressive one. So you see how they keep cycling.
Similar to poker.
Yeah.
You know poker.
Yeah. Yes. So here, well, you might wonder what happens here. Well, basically each species, if you look at each species on its own, it beats one other species and gets defeated by another one, right? So for each species, one of the Lyapunov exponents will be negative and one will be positive. So basically, in one direction you get attracted, and in one direction you get repelled. So that's why, in order to see if you go extinct or not, what you have to do is you have to see if overall you get more repelled or more attracted. So that's why if you multiply all the positive ones and then multiply all the negative ones and add them up, if it's negative, it means that you get more attracted to the boundary than repelled. So then we can show that there's extinction. Extinction in the sense that you converge to the boundary, but you won't converge to one axis. So you converge in a complicated way to the boundary. Okay, and if it's positive, then it means you get repelled more than attracted. So so we can show that there exists a unique ergodic measure, or invariant probability measure, which the 3 species converge to. So even though they're cycling, they will not go extinct, and they will converge to this invariant probability measure. And so those are all so this fully classifies what can happen with 3 species. Okay, so now I told you about one type of noise, these stochastic differential equations. But sometimes biologists are not very happy with stochastic differential equations. They say that it's somewhat unnatural. So I'll tell you about a different type of noise. So how do I introduce this noise? Well, first let me tell you about the competitive exclusion principle. So the competitive exclusion principle is one of the fundamental principles of ecology. What it says is that if you have multiple species competing with each other for the same resource, usually one will be the best at using up that resource, and it will drive all the others extinct. So in a way, the winner takes all. Everyone else dies. But however, when you look in nature, that's not what usually seems to happen. Usually you get multiple species coexisting, even though they all compete for the same resource. Right? So one example, you have plankton. You have tens, maybe hundreds of species of plankton. They all compete with each other, and there are just 2 or 3 resources, and yet they coexist. So that's why Hutchinson, when he saw this, right, experimentally, he called it the paradox of the plankton. Why is the paradox? Well, it seems to be violating this competitive exclusion principle. So Hutchinson was wondering how this could happen, and he gave a possible explanation. He said that maybe the variations of the environment can keep species away from extinction, right? So maybe one species is the best at using up that resource at one point in time, but then the environmental conditions change, and the different species is the best, right? So, and maybe that can keep species from extinction. So let's look at a simple example. You just have 2 species, x1 and x2. They're competing for one resource R, an abiotic resource. So if it's deterministic, if we just look here, this says that what happens with species 1? Well, if there's no resource, species 1 just decays exponentially, goes extinct exponentially at rate alpha 1, right? And if there is the resource R, then B1 tells us how efficient that species is at using up the resource. So if it consumes 1 unit of resource, then it gives rise to B1 offspring. And similarly for species 2, right? So B1 and B2 tell us how efficient they are. Of course, I have to tell you how R depends on x1 and x2. It's an abiotic resource, so the simplest assumption would be that that resource, so it always gets replenished, but it decreases linearly with the two species densities, right? So it has a maximal value R bar, and then it decreases linearly in x1 and linearly in x2. So in principle, it could even get negative. If it gets negative, it means that they have to wait a long time until they can use up some of the resource, right? So now if you plug in this into the previous system of differential equations, you just get this. And this is a Lotka-Volterra competitive system. However, it's a specific type of Lotka-Volterra competitive system because there's a certain relationship between the coefficients. Okay, and you can show here that it is not possible for x1 and x2 to both persist. One of them will go extinct. So so the competitive exclusion principle holds in this setting. Okay, so now we want to introduce some type of randomness. So, and the way we will do it is we say that there are two environmental states. You can think of it as summer and winter. So maybe the way the two species interact is different in the summer and in the winter. But we also don't know how long the summer and the winter are. So the seasons might be, the randomness comes from how long each season is. Okay? So you have two seasons or two environmental states. You start in one environmental state, spend a random time there, and to make things simple and make them Markov, we assume that this random time is exponential. Now, of course, if you want to model a system, it won't be exponential because the system won't be zero up from 0 up to infinity. But as a first approximation, you can model things using these exponential random variables. So you start in one, follow the dynamics in that environment for an exponential time, switch to the other state, right? Follow the dynamics in that state for a random time, and you keep switching, right? So you see the randomness comes just from how long you spend in each environment. Otherwise, so that's why these types of processes are called piecewise deterministic Markov processes, because the randomness comes just from how long you spend in each environment. Other than when you're in an environment, you just follow the flow of a differential equation. It's purely deterministic in that environment. Okay, so now the question is, what happens as time goes to infinity? Right? And to make things even more interesting, let's assume that in both environments, remember, I told you that it's not possible for x1 and x2 to coexist. So let's assume that in both environments, the same species wins. Right? So in environment 1, species 1 persists and species 2 goes extinct. So if you look at the trajectories in environment 1, everything converges to a fixed point on the x1 axis. X1 goes extinct. Environment 2, same thing happens. Everything converges to a fixed point on the x1 axis. X1 persists, x2 goes extinct. So now the question is, what happens if we start switching? Now, intuitively, at first, we say, well, the same species wins in both environments, so it shouldn't matter if we start switching, right? The same thing should happen. However, that's not what happens. So it's possible. So everything you can choose is how long you spend in each environment. So the dynamics in each environment is fixed, right? We have the dynamics in each environment. But if we choose the random times t1 and t2 carefully, we can show that the competitive exclusion principle fails, and you can get coexistence. So by spending time in both environments, there can be some type of rescue effect, which forces both species to persist. And actually, we can get something like this. You can get 4 different results, right? So according to how you pick the times t1 and t2, there can be 4 regimes. The first one is what we expect. The persistence of x1, which was dominant in both environments, and the extinction of x2. That's not, again, that's not interesting. The second one is coexistence. Both x1 and x2 persist. The third one is the least intuitive because it's a complete reversal, right? x1, the one which was dominant, now goes extinct. And x2, persists. Right? This is very counterintuitive. And then finally, you get something like bistability. So for some initial conditions, so depending on the initial conditions, with a certain probability, which is non-zero, x1 persists and x2 goes extinct. And with 1 minus that probability, the opposite happens. Right? So this, I mean, this is it's a nice result, but right now you won't, I mean, it's not clear why this can happen, and how we can do, I mean, how we can build a general theory, right? This is just a neat example, it's not the general theory. So I'll try to tell you a bit about the general result, and then I'll return to this example. So in general, we don't have just two species, and we'll be modeling things using piecewise deterministic Markov processes. So again, you have a fixed number of environmental states, a finite number, and each environmental state comes with its own system of differential equations. So it comes with its own dynamics, and then you can just switch between these finitely many environmental states. Okay? So it looks like this. Little r now keeps track of which environmental state you're in. So if we know that little r is little I, that tells us that we're in environment I at time t. So if we know in which environment we're in, we'll be knowing what the dynamics is. Okay? So we basically just have this system of differential equations, if you want, with the difference that the differential equations change with the environment. So that's why this fi here depends on little r. If you have a different environment, you have a different system of differential equations. So in order to fully specify the dynamics, I also have to tell you how little r switches. Like how does it change? What's the dynamics of little r? And we can make it complicated, but basically what we can do is we can model little r as follows. If we know that at time t little r is in state I, then the probability that in a small time delta it jumps from state I to j is approximately equal to qij, which is like a transition rate from state I to state j, times delta. And you can even make that transition rate depend on the density of the species. So it can be very complicated. It can be density dependent, but then we cannot compute anything. So in our simple example from before, when we were just spending an exponential time in each state, that's exactly when your qij's are constants. So they're not dependent on the densities. If they're constants, then little r is just a Markov chain, and it spends in any given state an independent exponential time. Right? Okay, so now what's the theory? We need to look at all the invariant measures, but now not just of x, we need to look at x and r. So the process is now x and r. You have to keep track both of the species densities and of the state the environment is in. So now the boundary of the state space is, well, where at least one species is extinct, but then crossed with the states of the environment. Okay. So you have all the invariant measures, and you know that the invariant measures are a specific type of invariant measure is an ergodic invariant measure, right? The ergodic invariant measures are the building blocks of the invariant probability measures. Okay, so the idea is just like what we were doing when we had stochastic differential equations. You pick some invariant measure, which kind of describes a subcommunity of species at equilibrium. And then you want to see what happens if you introduce a new species I into that subcommunity. Does it get repelled in that direction? So does it tend to go extinct, or does it tend to increase? So you just have to average. Now instead of averaging like we did for the stochastic differential equations, we have two types. We need to average over mu, but mu has a component which is due to the species, which is the integral. And then you also have to sum over all possible environments, right? So that's why the invariant probability measures keep track both of the species densities and of the environment. So that's why you have an integral and a sum. but really the intuition is the same as before. You take the log of xi divided by t, you get this term which goes to 0 when you let t go to infinity, and this term here, this integral average, you can show that this is approximated well by this if your process stays close to this measure mu. It seems stuck.
Yeah, it seems stuck, but here is. Yeah,
Is it working?
This is stuck, but this is moving.
Oh, so for just the screen here is stuck. Right?
Yeah.
È problematico.
Un problema del bloccatore nuovo che qua cambia.
Cavolo, anche lì.
Che cosa?
Del proiettore, forse è un problema di...
Il proiettore è collegato al wifi, non è attaccato al cavo. Just wait a second. Questo qua va, giusto?
Sì, quello è frozen.
Ok, your one is frozen. And you
No,
have...
No, it works now.
Yeah. And that one.
Okay, so again, the intuition is if there is an ergodic measure mu living on the boundary, it describes a subcommunity of species where at least one species is not present. So it describes the equilibrium state of a certain subcommunity. So the coexistence result is just analogous to what we had when I was telling you about stochastic differential equations, right? If for any invariant probability measure which lives on the boundary, at least one of these Lyapunov exponents or invasion rates is positive, then this mu is a repeller, right? So it basically mu repels you from the boundary. So if everything living on the boundary repels you, then you cannot converge to the boundary. So if this happens for every invariant probability measure, then the system is strongly stochastically persistent. So it just means that, again, don't have to go over this technical thing. Just means with high probability you don't you stay bounded away from and then because here things are more degenerate than when you have white noise. So these deterministic microprocesses can be very degenerate. So you need additional assumptions to actually prove that there exists a unique invariant probability measure. But under these extra assumptions, you can show there's a unique invariant probability measure, and just as before in the stochastic differential equation setting, you converge to this unique random equilibrium. Okay, I don't have that much time. I'll start to go a bit quicker. So I just want to give you the intuition. Let's say you just have 3 species, and you know that there is this invariant probability measure living on the x1, x2 plane. Okay, so we want to look at the invasion rates into this subcommunity. Now, if you look at species 1 and 2, these are, they basically live inside this invariant probability measure. They're supported by this invariant probability measure, so their invasion rates are 0. Right? If your species 1 and 2 are at equilibrium, so they don't tend to blow up or go to the boundary. Right? So they can be negative, they can be strictly positive, they're 0. So whenever we look at invariant probability measures, if we look at these invasion rates, we only care about the species which are not already in the community. Right? The ones in the community will always have 0 invasion rates. So in this setting here, if the third species has a negative invasion rate, we say that this here is a transversal attractor. So it attracts everything that's not in its support. And of course, I just have the same kind of definition, but I can't draw it for more than 3 dimensions. So a transversal attractor is just something which attracts everything which is not in its support. Okay, and now I can skip this orbit set stuff. We have the first extinction result. What does this result say? suppose there's at least one attractor on the boundary. And suppose you can get close to this attractor, right? Because again, because these processes can be degenerate, it might be the case that you can never get close to that attractor. So it doesn't matter if it attracts you. If you can get close to it, you can feel its attraction in a sense. Okay. So if you can get close to that transversal attractor, then it's impossible to have coexistence. So something will go extinct, but we don't know what will go extinct. So all we can say is, in this result, we just can say that the distance between the process and the boundary will go to 0 exponentially fast. Right? So this distance will look like e to the minus alpha t for large t. So you converge to the boundary, but usually we want more than just knowing that there's some extinction. We want to know exactly which species go extinct. So I'll go quicker. So this theorem tells us exactly what can happen, right? So suppose we have multiple attractors on the boundary, okay? So then for any attractor on the boundary which is reachable or accessible, right, which the process can get close to, then with a strictly positive probability, you converge to that attractor. Okay? So the species which are not supported by that attractor, they go extinct with a rate, an exponential rate of extinction, which is exactly given by these Lyapunov exponents or extinction invasion rates. And the species supported by attractor, by the attractor persist. So each attractor has this property, and then the probabilities have to sum up to 1. And the probabilities will also depend on your initial conditions. So, like I said, if you start very close to an attractor, it will be much more likely you get sucked in by that one. So this now tells us basically that these transversal attractors determine what happens. Each one, you have a specific probability of converging to one of these, and there's nothing else that can happen. Okay, so now let's go back to our example, and let me tell you how we get the various results there. So we have the two species, right, which are interacting according to that Lotka-Volterra system. But now the coefficients depend on the environment. You have two environments, 1 and 2. Each environment comes with its own coefficients, and now little r is just an independent irreducible Markov chain which switches between states 1 and 2. So now if we have a Markov chain like this, it will have a stationary distribution, nu1, nu2, which basically tells us long-term what fraction of time do we spend in environment 1, nu1. What fraction of time do we spend in environment 2, nu2. Okay, so now let's apply our general theory. So we start with the simplest community where everything is dead. Right? So that's the Dirac mass at 0. It's not quite just the Dirac mass at 0. Remember, we have to keep track both of the species and the environment. So the simplest invariant probability measure is the Dirac mass at 0 crossed with the stationary distribution of the Markov chain. But in any case, it's a very simple measure. It's easy to compute, so you can compute the invasion rates very simply for that. It's just an average of the growth rates, where the average is given by, by the fraction of time spent in each environment. Okay. If each of those invasion rates is positive, it tells us that each species can persist on its own. Okay. So that means that there is an invariant probability measure on this axis. There's an invariant probability measure on this axis. Now we have to look at the invasion rates of each species into the random equilibrium given by the other. So you can still compute explicitly lambda 1 of mu2 and lambda 2 of mu1. The others, remember, these internal exponents are always 0, so those are not interesting. And I didn't write the specific equations for these because they involve some complicated incomplete gamma functions, but you can still compute them. Okay. So then if both of those are positive, it means whenever you get close to the boundary, you get pushed away. And you get and if that happens, you get coexistence. But you actually get the 4 possibilities. The 4 different regimes are just given by looking at the signs of those invasion rates. So if this is negative and this is positive, this is negative, you get persistence of x1, extinction of x2. If both are positive, then you get that both of them persist. And then if you switch the signs, then you get the extinction of x1, persistence of x2. If both are negative, it means that both mu1 and mu2 are attractors. So with a certain probability, you converge to mu1. With 1 minus the probability, you converge to the other one. So that's how you get those 4 different regimes. And then you can prove algebraically that you do get all these combinations, right? So it's possible to get all these combinations of signs. Okay, so what's the summary? We were able to provide a rigorous foundation for a general theory of coexistence. We also proved on the way some conjectures of Chesson, Elmer, and Pallas. Now, future research would include looking at the effects of evolution, also including some type of spatial dynamics, so we didn't take space into account. And we can also try to do something similar if we look at epidemiological models, right? So that's it. Thank you for your attention.
Thanks. And do we have some questions?
In the one-dimensional case,
Yeah.
it converges to error.
Well, yeah, it will converge to. So in the one-dimensional case, it will converge to something which just puts mass on the x1 axis.
But the boundary is 0 in that case, right? The boundary for the one-dimensional case is 0.
Look, the boundary in the one-dimensional case.
Yeah.
So that just you look.
Plus,
yes. So that's why remember when we look at just look at the this axis, yeah.
Yeah.
The boundary of this is just 0.
It's 0.
Right. So that's why when you just look at one species on its own, you look at its invasion rate into the subcommunity of no species, the subcommunity that's the empty set, right?
Does not convert to the boundary.
No, yeah, it can, right? So
It can, but
yeah,
does not.
so if lambda 1 of the Dirac mass is negative, then there's no invariant measure here. So species 1 on its own, if you have a predator and a prey, for example, the predator on its own, it dies, right? If it has no prey. So yeah, then there would be no mu1 here, and you would just have mu2, and you still would just it's simpler in a way because you just look at whether species 1 can invade species 2, but you don't need to look at both. Yeah.
But there are also other examples in chemistry of
This type of behavior. Yeah.
this behavior can be applied to molecules, atomic or other entity other than population.
Yeah. There are, I think.
Especially chemical species can be applied. There are examples.
I mean, the examples I look at are usually from ecology, but I know
Ecology,
but these piecewise deterministic microprocesses, they've been applied in other settings, biology or not just biology, other settings. But I just don't know those settings that well.
Io chiedo io.
Immagino
che potesse essere.
I don't know. You mentioned at the end of your presentation, very interesting presentation, the epidemic models. But does the invasion rate as a relationship with the basic reproduction number of an epidemic and exactly with multi-groups populations with different kind of infective?
Yeah.
If there is a clear relations, or you are investigating on this topic, or you have an idea?
There are results, so you can do similar things in all these. Like, let's say there's no space or no spatial, but if you dynamics, you just have an SIR model. So there are SIR models where you can still do it. We're actually finishing. Here's my collaborator. We're finishing up a paper now where you look at SIQRS. That's a lot. Model
or quarantine.
Yes, yeah, and you have well, we made it more complicated. You have both the white noise and the switching, and you can still, so you still can show that there's a threshold given by such an invasion rate, which determines whether the disease persists or goes extinct.
Yeah, exactly, because for the reproduction number, there is the threshold that is 1.
Exactly, yes.
For the invasion rates is 0, but
Yes.
the invasion rates is a log quantity, so
Exactly,
maybe it's
yes.
the same thing.
Exactly, yeah.
Thank you.
I also have a question.
Yeah.
Quite recently, Federico and I were involved in research when we have a stochastic tumor model, and we had this problem of evaluating the extinction probability, which is more or less the opposite of having like coexistence of. And the framework a framework that we're building was based on continuous time Markov chain. So also species, and not only the environmental states were connected by a Markov chain. I know that, I mean, from the computational viewpoint, is a mess, but usually what we saw is that maybe there is one species you're interested in, so you consider the ODE equilibrium for n-1, and then you can study a simplified version for one species in a discrete version. So this could be maybe, I mean, a variant of this when you address at least one population to evolve discretely on space. Does a kind of persistent or extinction theory for this kind of model that evolve discretely on space?
Yeah, no, so that would be one.
One further
yeah, if you
path
include
of
spatial
research.
dynamics, is very complicated. But so if you include spatial dynamics, for example, if you instead of having SDE, you'd have SPD, so stochastic partial differential equations, which are very hard to look at. But we're trying, at least in simple settings when there's space. Let's say instead of having like a real spatial spread, you might have a number of patches, and you just move between these patches. So discrete, like discrete space like that. Then I think you can do stuff like this.
Because I mean, in that case, you get rid of the Brownian motion,
Exactly,
but you only, I mean, you should rephrase in terms of transition propensities or probabilities, and so that where the noise comes from. There is some kind of compatibility conditions between SD and continuous time Markov chain, but there is also something that is not perfectly matching. For example, the finite time behavior.
It's
usually is different. You can have an extinction in finite time, and maybe you can evaluate the time on Markov chain, and not the same for the continuous version. So
yeah, of course. So here, the type of stochasticity we looked at here is the so-called environmental stochasticity, right? So that's why you can never have extinction in finite time here, but you can also include demographic stochasticity. And if you include demographic stochasticity, then everything goes extinct in finite time. But this is still relevant because so when you have extinction that everything long term is dead, you can still look at something called, instead of the stationary distribution, you can look at the quasi-stationary distribution. So then you condition on not going extinct up to a certain time and look at this condition process. And it still tells you something about what happens before extinction. So because it will look like the population, it might have a long time transient before it goes extinct, and you want to say something about that transient. So we're able to show that if you have both environmental and demographic stochasticity, and you start making the environmental stochasticity smaller, so there's a relationship between the quasi-stationary distributions and the stationary distribution. So you can show that even in a sense here, it's not realistic that extinction only happens as time goes to infinity. It's a good approximation of what happens. So this still tells you in a way what happens with the system when there will be finite time extinctions.
Okay, great.
It has been applied to fishing, this theory.
Fishing,
It seems important for
Well,
fishing.
well, yeah, the same. Actually, that's like one other side of my research is looking at this, but then you also include harvesting or fishing. And then the question is, how do you? What's the optimal way in which you can fish so that you don't drive the population extinct and you gain the most economically? So
When you can fish.
Yes. When you should and when you should, and how much you should, and so what's the optimal strategy? So yeah, we've actually been working on that as well. Yeah.
Okay. Are there any questions from the audience online? Maybe not, or maybe yes.
Well,
Yeah.
can you hear me?
Yes.
Yeah. Some.
Alessandro, can you hear me?
Yeah.
Yes,
Now,
yes.
yes.
Yes. So, well, first of all, Alexandru. Yeah, right. Now, I'm talking, there are too many Alexanders here. So, Alexandru,
Yes.
thank you very much for your very complete presentation.
Thank you.
When you introduce stochasticity, by the way, Teams is a disaster as far as I am concerned. But okay. So if I say something very stupid, please, it's Teams' fault. All right. You introduced this in the first place.
Yes.
By going to an Ito differential equation.
Yes.
And then you said by so now we're very happy with kind of generated to an Ito, with which position I can sympathize very much. Correlated noise.
You're breaking up. I couldn't hear that half of what
Andrea, can I call you on the mobile phone so maybe we can have a better chat?
We are on the
Yeah.
Yes, we are on the mobile phone as I speak.
Yes.
Question slowly.
Yeah.
So how do you deal with autocorrelated?
Andrea.
Write it in chat.
They're going to call.
Andrea.
Alessandro, dimmi.
Yeah, you are live
on the phone.
On the phone with also with our speaker, so you can ask the question.
Hi.
Because the connection was very bad.
Hi.
No, really, I must repeat my statement of before. I've been at Teams is a scourge of an application. Apart from that, you introduced noise using either differential equations.
Yes.
Biologists are not very happy.
Yeah.
And I can understand why. So my first question would be, how do you deal with autocorrelated noise?
Yeah. Well, yeah. You need different models for that. We're able to do that by introducing. You can introduce another variable. You can introduce a variable like an auxiliary variable, which.
It is clear.
Yes. So.
Alexander, that's clear. But if I had, for instance, if I had to introduce a sufficient degree of autocorrelation, I may need more than one condition variable, right?
Yes.
And I might need to chain them, right? One after the other, right?
Right. Yes.
But then I would have to estimate, if I go to data analysis or parameter estimation of these kind of models, if I have several, say, compartments, separating my noise generating system to the actual observation I make, I will need to estimate many parameters, would I not?
Yes, I mean, yeah, the estimation would be complicated. But
Yeah, and that would be that would be a drawback.
yes, I mean, the thing is that even in this setting, if you don't have any autocorrelation, so even if you have more than two species, I mean, the whole theory is based on these Lyapunov exponents, but you can't compute. So that's why my example was for two species where I can compute them. So even for two species, there needed to be 3 papers where people actually computed these Lyapunov exponents.
Per species.
Yeah. So computing the lambda, just computing the lambdas is non-trivial. So even if you don't go to the estimation problem, just computing the lambdas is, I mean, analytically you can do it for more than 2 species. So then even for those you'll have to do some kind of simulations or Markov chain Monte Carlo or something like that.
And this is, again, part of my question. I hope I'm not boring anybody. I will shut up in about 2 minutes. So just a couple questions more and I'll shut up. Next point is, did you ever analyze real life data? And in this case, how did you proceed with the estimation?
I have a simple answer. No, but I mean, we're looking into this. Yes.
Last question, absolutely last question. Suppose you have a known Markovian system.
Mm-hmm.
What then?
What do you mean by a no? Non-Markovian. Oh, okay. I thought you said known. No, you non-Markovian. Non-Markovian. Yeah. So. If you remember from the talk, I picked the exponential times. So the times.
Yeah, that's clear.
That I picked it. I mean, we picked it for a reason like that, so that it can be Markovian. But we can also do it if we don't pick those times to be exponential. You pick them from some other distribution, and then you get something non-Markovian. You get a semi-Markov process, and you can still do it by you can still analyze that. So it depends, and it depends on what processes are. But
Alexandru, the point I'm trying to make is that if you have a non-Markovian system, assuming you can do the theoretical analysis that you're talking about, which is fine, but if you have a non-Markovian system, then you do not have, or I do not know that you have statistically correct parameter estimation procedures. That was the point of my question. What would you do then in order to estimate parameters?
Well, I think we didn't look at any data. That's like I said, we're even though the problems are all coming from biology, all we've done up to now was prove theorems. So I admit that we don't know much. I mean, I personally don't know much about the parameter estimation. But so we need to team up with someone like you then.
The blind consorting with the deaf.
Yeah, exactly. Through Microsoft Teams.
Exactly. Yeah. Everything is fine. Great, Alexandru. Thank you very much.
Thank you.
Okay. So if there are no other questions, I would close the seminar, and I would thank our speaker again.
Grazie. Grazie a tutti.
Grazie a te e a voi. E ci vediamo alla prossima puntata. See you next time.
Are you Romania?
Yeah.
Alexandru is the son.
Yeah. Yes.
The name.
The first name, not the last, not the family name.
Not the family name.
Yeah, family name is by the family name I sound German. People won't. They can't tell. Yeah, they can't tell I'm Roman. But when you see Alexandru, that's always a giveaway. It's only Romanian.
Alexandru is your first name.
Yes.
Thank you. Bye.
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 No, non so se questo...
Cosa?
Se lo devo andare
Questo qua?
da Tiziano.
Di solito ultimamente non c'ho. Well, it's the first time I give a talk through Teams.
Your first time?
Yeah, and last time, you know.
No, yeah, but it could be also. Yeah, since also the laptop was not very responsive, so I get to could also introduce some lag with the.
But he wasn't very happy with Teams. It seems like he doesn't like it. I don't, yeah.
Poi passi da me 2 minuti.
Okay. Yeah, now I can. Yeah, it was. I mean, it was.
Even though it's not what everyone's doing necessarily, but
Yeah, because Andrea was the guy that you contacted some time ago.
oh yeah,
Yeah.
But
Yeah.
he's not based here.
Yeah, but since he's on a mission today, he's traveling.
Oh, I see.
Yeah, so he probably called from a very bad place.
Like from the airport or something.
In the south of Italy. Yeah, he was, yeah. So it could be that.
He was the problem.
Yeah, he blamed Teams, but I think that the problem maybe was him. Yeah, and. Yeah, because before you met